chapter 3.5. We're jumping around a little bit because I want to go grab these limits at infinity. That's what we're going to study here. Mainly trying to find if there is a horizontal asymptote to the function. So if we look out at infinity, we may discover that. Let's just quickly review where we've come and where we're headed. So earlier in this chapter, we looked at graphs and tried to determine limits from graphs. So I looked at if this limit is approaching, as x approaches 1, from the left and from the right, I am coming into 3. We also did it in a table format. Filled in the table and notice that these indeed are coming together, and it appears that they're going to reach a height of 3. And then algebraically being able to work the factoring technique so that we can get around the denominator that went to 0 when we substituted 1 in and plug in now. Now I can use substitution once I was able to get around this denominator issue. So that's where we've been. Now let's look at what the limits at infinity are all about. Well, when I move out to infinity, I've got x values that are headed, out here in far to the right. And what I'm trying to see is, does this function settle? Does it ride along a value? Is it getting close to some value and staying there? And if I look at this picture, I would say yes. I think as I move to positive infinity, as x moves out to positive infinity, it appears that I do have a limit at this height right in here. As I move to negative infinity, so negative infinity, way far to the left, it appears that this function is settling down too and riding it out. Horizontal asymptotes, here's the definition. The limit as x goes to negative infinity of some function is equal to L. If I get a number here, that will represent my horizontal asymptote. It becomes the equation y equals L. Likewise, if I move to positive infinity and I approach some limit, L, I have a horizontal asymptote. So y equals L. Is called the horizontal asymptote. A quick theorem for a specific style. If R is a positive rational number and C is any real number, then I would be able to say the limit as x approaches infinity of some real number C divided by x to the R power, where R is positive, so this x to the R stays in the denominator. I would have C divided by x to the R, and this number would get quite large. And that is going to make this go to 0. So the limit is 0. Likewise, if I'm going to negative infinity, it too will approach the value of 0. The limit is 0. So A, B, and C are demonstrations of this theorem. And we have some number 5 divided by x to the 7th. 5 divided by something raised to the 7th, and I'm letting x get really large. So I have a large number raised to the 7th. Well, that's even going to get larger. So I have 5 divided by a very large positive number. That's going to make this go to 0 just by that same theorem. We see it. But you can think it through as well. On the next one, I'm moving to negative infinity. So I have 5 divided by a very large negative number. 5 divided by very large negative will give me a negative number, but it's going to be like, 0.000000099 maybe. It's still approaching 0, but it's coming from an underside of the, well, if we're moving to negative infinity, I should write this the other way, shouldn't I? Maybe my function, as we're heading out, is going to approach the x-axis from underneath side, from the negative side. But still, it's coming into 0. The last one, I just want you to recognize that you can break this into two limits. Addition and subtraction of two terms, I can split it up and do the limit of the first term minus the limit of the second term. And the limit of a constant is a constant. That's going to be 6. So the limit as x moves to infinity of 6 is 6. And this other one is a demonstration, once again, of this theorem. 4 divided by something super large, some big number, is going to make that go to 0. So my limit there is 0, giving me an overall limit of 6. Rational functions, let's find the horizontal asymptotes. The technique for finding these limits at infinity, divide each term by the highest power found in the denominator. So letter D here, I'm looking at my denominator and I notice the largest power I see is 4, the x to the 4th term. And I'm going to take and divide each of my terms by x to the 4. On top, I've got x cubed over x to the 4th minus 4x divided by x to the 4th over 2x to the 4th divided by x to the 4th plus 5 divided by x to the 4th. Simplifying the limit as x approaches infinity. On the top, I'd have 1 over x, because that'll simplify. The next will be 4 over x cubed. On the bottom, the x to the 4th cancels, so I'm at 2 minus 5 over x to the 4th. Now, as I approach infinity, insert a large number. 1 over large will go to 0. 4 over large will go to 0. So on top, 0 minus 0 equals 0. On bottom, the limit of a constant is the constant. 5 divided by large will go to 0. I have 2 on the bottom. This will give me a limit of 0. What have we discovered? We've discovered a horizontal asymptote at y equals the limit, or y equals 0. So we get a horizontal asymptote at y equals 0, which describes a horizontal line, y equals 0. Letter E, very similar application. Look at your denominator. I do see a radical in this denominator, but inside that radical I see an x squared. So what I want to do is I want to take care of that one. I'm going to divide by that highest power. So I'm going to rewrite this problem just so I can make more space. We're going to negative infinity as well. I just picked that up. And give yourself a little room there underneath your 2x. Drawing in a little bit larger radical sign, I've got x squared minus x. I'm going to take and divide each term by that x squared. And on top, notice that this has a radical over it, radical of square root of x squared, which truly is just x, isn't it? So now let's simplify. Change color here. Let's simplify this out. We have the limit as x approaches negative infinity. 2x over x divided by radical or square root. That would be 1 minus 1 over x. If I let this go to infinity, we know this is canceling. This limit will be 2 because the limit of a constant is itself 2. Limit of a constant will give me 1. So I'd have the square root of 1 minus, this is going to 0 minus 0. So here I have 2 divided by the square root of 1 gives me a limit of 2. But hold on, we do have to be careful with negative infinity because sometimes that negative will slip away on us, especially when we're squaring things and then dividing by that power. It took that x term away. Go back to the beginning, go back to the original, and substitute in a negative and see what happens. Go back to original to test for the negative, because we're working on negative infinity. So if I just took 2 times x and I put in negative infinity or a negative large number, this would be a negative value. On the bottom, I have the square root of a negative being squared minus another negative. Well, that's going to turn out to be positive. This is going to be positive. It's all pluses in the bottom, negative on top. That's going to yield a negative. My answer is actually going to be then -2. So on those type of problems, just know you really need to go back and do an analysis on the positive negatives to determine the outcome. All right, there are shortcuts where we don't have to divide by the largest degree of the bottom like we had just demonstrated, for instance, that. There is a shortcut, and that is to compare the powers of the highest degree in the top and the power with the highest degree on the bottom. And when I look at this one, I notice that 6x squared would be my highest degree term on the top, and 3x squared is my highest degree term on the bottom. I'm going to compare those two and take their coefficients, because the degrees were equal, and simply divide out those coefficients. My limit is 2. I know there is a horizontal asymptote at y equals 2, as demonstrated in this graph. So this case was when the power of the numerator, or the highest power in the numerator, is equal to the highest power in the denominator. And then we can simply compare the coefficients. So now compare, or really you divide, let's say that. Now divide the coefficients, and that will give you your limit of each of those terms. Case number 2. When the degree in the bottom is higher than the degree in the top. The highest degree in the numerator is less than the highest degree in the denominator. When that is the case, my denominator is going to be dominating this function. The denominator grows more quickly. So if that's the case, if this is growing larger faster than what the numerator is, I would have this thing going to 0. So the limit is 0. And you can see that in the picture here. I've got an asymptote on the x-axis. Here, this function, as it goes to -infinity, is riding along the x-axis, and same is true there as I head to +infinity, riding along the x-axis, or y equals 0. Y equals 0 is my horizontal asymptote. Case number 3. When the highest degree in the numerator is larger than the highest degree in the denominator. Let's look at that scenario. Highest degree of numerator is greater than the highest degree in the denominator. By more than 1 degree. Because something special happens when it's exactly 1 degree. By more than 1 degree. When this is the case, my numerator, notice the numerator is growing more quickly. Is growing more quickly. Thus, it is going to take over the function, and this function is going to equal +infinity, or perhaps negative infinity, you'll just have to check out your signs. On this particular problem, I would see x to the fifth. If I put a large negative in, that's going to stay negative. On the bottom, this will be negative, resulting in positive. This function is going to go to positive infinity. So there is not a horizontal asymptote, but I do know that the end behavior of this function as I head to negative infinity will be sweeping upward to positive infinity. And finally, the fourth case, the degree of the numerator is exactly 1 degree greater than the denominator. We can use long division or perhaps synthetic division if the problem lends itself to that. And in this particular case, it does. This gives you the equation of the slant asymptote. When does a slant asymptote occur? When there is exactly 1 degree difference between the numerator and the denominator, and the numerator is larger. So we can go into synthetic division. There's my number that goes in the box. Copy your coefficients down, putting a placeholder in for the x term that didn't exist up here in the numerator. Drop your 1, multiply. 3 times 1 is 3. Add these values. Gives me 3. Multiply. 3 times 3 gives me 9. Add 7 and 9, you get 16. But I can drop this off, ignore that, and this gives me a linear equation of 1 degree less than what I started with, so I'm down to an x plus 3, and that describes a slant asymptote. Okay. This screen does a little bit of a summary of what we just went through. When the degree of the numerator is smaller than the degree of the denominator, the limit will be 0 because the denominator is dominating this function and grows more quickly, taking the overall function to 0. When the degree of the numerator is equal to the degree of the denominator, your limit is the ratio of the coefficients that lead those highest degrees. And the degree of the numerator being greater than the degree of the denominator, the limit does not exist. The function is going to tend off to infinity or negative infinity. And I think that's all I have time for.